Welcome to Year 1 Mechanics, Chapter 11.2, where we continue with variable acceleration, where we talk about functions of time last lesson. So here's a scenario. Okay, now before we write any notes, anything, just understand what we're trying to do in here. And you can have a look on a topic about differentiation, but we first understand why differentiation is related to acceleration or mechanics. Right, so here's a scenario. Okay, you're a sensible driver, sensible driver. Okay, so that's you, okay, driving a car, okay, and then you see a traffic light, okay, that was green, that was green, okay. But however, as you're approaching the traffic light, okay, you see the traffic light start to turn yellow. What would you do? Not speed up, slow down, decelerate, right? However, we know in real life, okay, in real life, we don't decelerate consistently. Even though as much as we want to decelerate every second by the same meter per second squared, we know it's impossible because we are human feet. By putting a little bit more force on a pedal means you decelerate more, you brake harder. By putting it, off the pedal means you're not braking it. So, so we know, that's if we have a constant deceleration, that will be it. That's a VT graph. Okay, that's a VT graph. I'll show you the notes. This is not the notes. This is just illustration of a situation. So that's more like a constant, constant deceleration, deceleration, right? However, in real life, we know what will happen is we'll go closer and closer to the traffic light. Okay, and then what we do? We brake a bit harsher, right? So that will be a more like a real life scenario where this is a variable deceleration. So it's a curve. Can you see it's a curve, right? And what happened if you're blind? If you're a blind driver, what happen? If you're blind, obviously that means you're going that way. You're not slowing down. Whatever people crossing the road, you treat them like a bowling pins. You just run them over. Of course, you don't want to do that because you'll be in jail. So, right. So that's what we're talking about. Okay. When we talk about variable deceleration, you can think about in a curve. When it comes to, if you remember about acceleration, is the gradient for a VT graph. Gradient relates to differentiation. And that's why when you have to work out a gradient of a curve, that relates to differentiation. Okay. So that's how it all comes together. All right. So that's the notes here. Okay. So here the notes we'll talk about. So this one, let's bring it over to the Let's bring it over somewhere. Okay, so here are the notes. First of all, let's look at the ST graph, displacement time graph. Okay, so in real life, oops, can't spell. In real life, where we have variable acceleration. Okay, acceleration. So with ST graph in here, ST. So what happened is it's a curve. So the gradient, okay, the gradient is velocity. Right? We know that the gradient is velocity, and gradient can be found can be found using differentiation. So if you imagine a x and y axis, then the gradient will equal to dy by dx, right? So therefore, in a ST graph, you can imagine the gradient will equals to ds by dt. So therefore, velocity in ST graph equals to ds by dt. So v equals to ds by dt. That's the first takeaway home message. Okay. Next one. What about the VT graph? In the VT graph, okay, okay, let's imagine we accelerate. Okay, we accelerate on the traffic light. Now, to be honest, the graph, I mean, the shape of the graph does not matter as long as it's a curve. What I'm trying to show you is, let's say we accelerate from a traffic light, when we accelerate from traffic light, it's either way how you want to draw it, to be honest. It doesn't matter which way the curve bends. So VT graph, as long as we're showing it's a variable acceleration, we know it's a variable acceleration because it's a curve, right? Okay, so similarly, okay, gradient, what did I write last time? Gradient equals acceleration. Okay, so therefore, so gradient equals acceleration, and gradient, so m also equals to dv by dt. So what does that mean? That means acceleration equals to dv by dt. Okay, so that's one take home message. Okay, okay. Now if we continue to do some more maths in there, okay, since v equals to ds by dt, so therefore, if we differentiate v, then it becomes d squared s over dt squared. So v equals ds by dt, differentiate again gives second derivative. Okay, so differentiate again gives second derivative. So look at pure one again. We mentioned about second derivative in here. So what does that mean? So that means a equals to dv by dt, but dv by dt also equals to d s squared, d squared s over dt squared. That means if you differentiate twice, it gives you acceleration. So ultimately, what we carry is a equals to dv by dt, or a equals d squared s over dt squared. Now, in normal maths, mechanics, not about further maths, we normally use dv by dt. You rarely use second derivative. So yeah, okay. So these are two technical messages. What we know is v equals ds by dt. To find velocity from a variable acceleration displacement. So when we talk about s, we can differentiate s with respect to t to find acceleration. To find a, we can differentiate v. All right, that's what we need to know. Okay, so now we know that. So let's write down. So we know s equals dv by dt, and a equals to wrong way. Sorry, v equals ds by dt, and a equals to dv by dt. That's what we need to know. All right, so let's read a question. Example, particle is moving horizontally. The displacement s from the original point is given as s equals t squared minus 3t squared plus 6. Now, hopefully I did mention it in the previous video. When we see an equation like this, we know it is not constant acceleration. It's not constant acceleration. If it's not constant acceleration, what does that mean? That means suvat not applicable. Okay, so we can't use suvat, okay, when the acceleration is not constant. How do we know it's not constant, you may ask? Because you can see the t is a curve, right? S is a function of t. So t is a curve, it's not a straight line. So part A, find the velocity after 3 seconds. So we'll find v. To find v, we can use v equals ds by dt. So we can differentiate s. Differentiate s gives you 3t squared minus 6t. And then when t equals 3, because we want to find 3 seconds, so v equals to 3 times 3 squared minus 6 times 3, which if I use my mental maths, aka the calculator, I get 9 meter per second. Right? Easy peasy. Part B. Find the value of t for which the particle is instantaneously at rest. Now, think about S, V, and A. Okay, displacement, velocity, acceleration. When a particle is instantaneously at rest, what can we relate? When a particle stop, okay, when you're running, okay, when you're too tired to run a 1500, let's say in a sports day, okay, or 2000 meters in a sports day, okay, you're too tired, you stand. Does the displacement change? No, your displacement, doesn't the displacement will be affected. However, it's not directly affected by instantaneous rest. When you instantaneous rest, it means the velocity is 0. That means the velocity equals 0. That's what it means. Instantaneous at rest. That means when v equals 0. Now, this will happen quite often in mechanics, so pay attention to that. When it's instantaneous rest, it means the velocity is 0. Okay, so v is 0. So we know 0 equals 3t squared minus 6t. So we should factorize the t, or essentially put in a calculator, you should get t equals 0 or t equals 2. And that's the answer we need, because t equals 0 means the particle started from rest, which makes sense. So t equals 2. Part C, find the acceleration of a particle when t equals 5. To find the acceleration, we can use a equals dv by dt. So we can differentiate v. So make sure you don't differentiate the wrong equation. You won't differentiate v. So differentiate this one, which is 6t minus 6. When t equals 5, when t equals 5, acceleration equals 6 times 5 minus 6, which is 24 meter per second squared. That's amazingly fast. 24 meter per second squared. Right, hopefully that's not too difficult. So practice question one, okay? Have a go at the question. Remember, it's all about these two equations here. B equals ds by dt, A equals dv by dt. Pause video, have a go at the question about Garfield. I don't think it's relevant anymore. I don't know if the generation nowadays know, or any now know about Garfield. Pause video, have a go at the question. When you're ready for the answer, you can press play. Here are the answers. A is negative 30 meter per second squared. I mean, meter per second. B is 4 and C is 27. Okay, question A. If you got it right, well done. That's the end of lesson. Yes, bonus. A short lesson. Otherwise, let's have a go. Okay, question A. So we're given S, the displacement is there, so that's the S equation. Given to find the velocity, so to find the velocity, we can do V equals ds by dt. Differentiate it, so 3t squared minus 3t minus 36 because that's squared and a half cancel out. So when t equals 2, you sub it in, you get v equals to negative 30 meter per second. Now, what does negative 30 tells you? It means the Garfield is essentially moving backwards. Okay, so maybe cats, they like running away from house every day, certain time of day, and then go to neighbors to get some snacks, and then come back to ask you for more food, etc. So maybe this one is where the cat is in your neighbors and then coming back to home. So that's why it's negative. Negative means coming backwards, all right? Part B. What time is instantaneous at rest? Instantaneous at rest, I just mentioned, V is 0. So when V is 0, 0 equals 3t squared. Oh, pardon my writing. 3t squared minus 3t minus 36. Put in the calculator. Showing how to solve a quadratic equation give you no marks. So don't think you are super smart to know how to factorize or use quadratic formula. In front of A-level examiner, they mean peanuts. Means nothing. So put in a calculator, you get t equals to negative 3 or 4. Obviously, you can't have time being negative. Okay, so time is 4. Part C. What is the cat's acceleration after 5 seconds? So we would find A, right? To find A, so A equals to dv by dt. So differentiate again, so give you 16 minus 3. When t equals 5, then acceleration equals 6 times 5 minus 3, which is 27 meter per second squared. Oops. Okay, right, and that's it. Bye.